So in this video, we look at the concept of a row space of a given matrix M. And now please view the matrix M as an array of numbers listed by the rows. So it's like it has row 1, row 2, etc. for the whole matrix. And the row space of a matrix M is defined to be the span of all the row vectors, right? Because we can actually view each row as a vector now. So I'm talking about now is the span of all these vectors. And let's look at the simple example first. So please look at the given matrix M, and you see now basically you have two rows. So basically you have two row vectors, which is 2, 1, and the second row is 1, 1, right? And you see because there are only two coordinates for each vector, it basically means the row space of M basically must be a vector space sitting inside R2, right? Because of the fact that both vectors, we can view them as in R2 in the XY plane. And now, the remaining fact to describe the row space is you have to really try to look at the spanning set of these two vectors. Can you describe this spanning set now? You see, for any vector subspace sitting in R2, the best way to think about is you can look at the determinant first. Especially now, in this case, you are actually getting 2 by 2 matrix, which is square, and we can take a look at the determinant. And determinant now is non-zero. And based on the last couple of videos, we understand that in the case of given two vectors, and also R2 is two-dimensional, we understand the two given vectors are actually forming a basis of R2. So what does it mean? It simply means that the span of these two vectors are actually the same as the whole vector space R2. We can actually describe the row space of the matrix M as follows. So basically now the row space of M is basically the whole space, the R2. You can think of it like this. And let's look at another case. Please look at the 2 by 2 matrix, and now you have the first row vector, which is 1, 0. And the second row vector is 2, 0, right? And I think both vectors, of course, are in R2, so it means at most it is a two-dimensional space. And I think we can easily notice that the second vector is along the same direction as the line generated by the direction of the first vector, because the R2 is basically 2 times R1, right? And it means they are on the same direction along the x-axis, basically, if you look at the xy plane, right? And it means what? It means there's no chance the given two sets of vectors actually span the R2. There's no chance because we usually need two vectors of different direction to span the xy plane. And this case means what? It basically means the span if we try to describe it. Because by definition, the span now contains all the linear combination of the two vectors, right? And because of that, this one has the same direction as this. Basically, I'm talking about just the line, which is exactly the same as the x-axis. And because that's the direction for the two vectors we have, right? Basically, it means the spanning set of these two vectors is simply the strict line having the same direction as the two vectors we have. So you see, of course, a straight line is one-dimensional, right? So we can think of the row space of M as follows. You can say that the row space is basically a one-dimensional subspace in the xy plane. And to be more precise, one-dimensional subspace is essentially the strict line that has this direction, which is governed by the direction you have in the row 1 or the row 2. And let's look at some notes here. So it's actually quite an interesting observation. I'm claiming that the row operations actually doesn't change the row space of any matrix. To convince you, we can look at some examples now. Let's say now I'm giving you such a 2 by 2 matrix. And let's say if you carry out certain row operations, let's say what you do is row 2 minus 6 times row 1 for the second row. Then you'll get a new matrix M prime. You can call it M prime. And now, based on my note, the row space of the two matrices shouldn't change. And although the matrix M prime, of course, now is not the same as the first matrix, right? Let's look at the row space of the two cases. For example, for the first one, if you look at row 1, which is 1, 3, the row 2 is 6, 18. And we easily notice that, of course, both vectors are in R2, and the fact is the row 2 is 6 times row 1, right? It basically means they are along the same line. If you look at the xy plane, they are basically along the same line like this. So row 1 and row 2 are sitting on the same line. And in this case, of course, these two vectors are not spanning R2. And this case is like a one-dimensional subspace in R2. And that's the row space of our current case for this matrix M. And let's look at the new matrix M prime. Now you see the row 1 is basically 1, 3, and the row 2 is a 0 vector. So it doesn't add any information, right? So essentially we can forget about the second vector. And of course, due to the fact that we have only one vector, and if you look at the span of this single vector, because the second vector is a 0 vector, it doesn't add anything. And of course, it basically means, based on this vector, the span is basically just containing the vectors like the multiple of the row 1, which means basically it covers the whole line, which has the direction same as the row 1, right? So basically, you see, if you look at the left and the right side, both are the same line, basically, you see? And the direction of the line, of course, is the same because the row 1 direction is not changed, right? And it gives you a sense that just based on this simple example, we don't expect the row space to be changed as long as you are just doing some row operations. And based on this fact, we can understand the row space a lot better if you are given a much bigger matrix. Please look at the following case. Let's look at the current matrix here, and let's look at the size of the matrix. It's 4 by 6, right? Basically, it means you have actually 4 row vectors to look at. And you see each row vector has 6 coordinates. So what does it mean? It means if you look at all the 4 vectors, they are sitting in the 6-dimensional space because of the fact that each vector has 6 coordinates. And because you have only 4 vectors, so at most the span of this set, a 4-dimensional subspace in R6, right? And obviously the span of only 4 vectors cannot span the whole space R6 because R6 is 6-dimensional. But if you're spanning like 4 vectors at most, you're arriving at 4-dimensional subspace. It can be less. It depends on the relations among the vectors here. And the last note I told you already, you're free to do some row operations on the matrix M. It doesn't change the row space. And although this matrix is big, but we still can do some row operations, right? For example, you can actually notice that row 4 is quite the same as row 1, but it's just the difference that each entry has a sign change, right? So basically, row 4 is minus row 1. So I'm using this fact to carry out the row operation for the row 4, like row 4 plus row 1. And in that case, we are left with a 0 row in the last row. Right, and please look at the similarities of row 2 and row 3. They are almost the same except the last 2 spots. You can take a look here. So it gives you a sense that we can actually do some row operations on the row 3. And the row 3, what we can do is something like row 3 minus row 2. And we can leave the row 2 unchanged for now. And the row 3, we should have a vector which is 0, 0, 0, 0 for the first 4 coordinates and 1, 5 for the last coordinate, right? And let's try to reduce something for the row 2. And I think we can carry out row 2 minus 2 times row 1 for the updates of the row 2, right? So you can take a look at the reduced matrix now after a couple of row operations. I think it is easier to understand now. You see the last row, but basically now is a 0 vector, so it doesn't add any information to us. And you have to take a look just by eyeball to see whether the 3 vectors here, row 1, row 2, row 3, are spanning a 3-dimensional space. I think it's quite obvious, you see, because for example, the last vector R3 here has only non-zero spots in the last 2 entries, and for the second vector has the non-zeros for the last 4 spots. It means you cannot generate the first row based on the last 2 vectors, right? So it kind of give you a sense that in this case, all 3 vectors are independent if you try to think about that. So there's no relation between the 3 vectors here. And it basically means we expect that the span of the row space of the matrix now should be 3-dimensional. Let me put it here. And also due to the fact that I've said it already, the row operations never change the row space. So even if now the matrix is changed, the row space itself is not changed, and claim that now the row space of our original matrix M is actually a three-dimensional subspace.